Alright folks, so we're continuing on here in chapter 6.7, discussing the confidence interval for a difference in means. And in the previous videos we saw the formula to create this confidence interval and a particular example. And in this video we're going to talk about some of the assumptions that have to be made for that confidence interval in a difference in means to be valid. So here's a couple of the requirements or assumptions that sometimes need to be made, and there's an additional one that I have not yet written. So some of these requirements here are going to look familiar because this is basically an extension of the conditions that were needed for a confidence interval for a single population mean. So let's take a look here. Remember that we are using sample data to infer or make conclusions about a population. So it's required that the samples be considered randomly selected to minimize bias in the selection process. And another requirement here is that the values are considered independent. So I kind of just put two conditions there into one. This next condition here is the one that takes a little bit of work. So because we are looking at a difference in means, there is a corresponding sampling distribution, and we haven't really discussed that, and we're going to kind of breeze past it. But we saw this with the single confidence interval, that this corresponding sampling distribution should be considered normally distributed. So how do we check for that? Well, if you've got the raw data, then you can use R to create QQ plots to check if those samples are normally distributed. So we can check with QQ plots. That's one way to verify that. Another way that we can verify if this requirement has been met is by using the CLT. Do you remember what that stands for? That is the central limit theorem. So if your samples do not appear to be coming from normally distributed populations, then we can utilize the central limit theorem, which states that regardless of the original distribution of the population, its corresponding sampling distribution will be approximately normal for sufficiently large sample sizes, i.e., for us, we're saying at least 30. Now, these don't both need to be met, so this is more of an or situation, so I'll say or. So we'll look at an example of that in a brief moment. The last requirement here is that the selection process of the two samples was done so independently, so selected independently. Now, that means that if you've got two random samples, that the selection process of one sample does not have any bearing or was not dependent upon the selection process for the next sample. What we're going to do in the near future, maybe in a couple weeks from now, is we'll see when this is not met, what do we do? So to contrast for right now, let's look at some examples in which this would not be satisfied. We're going to look in the future of paired sampling. And this is when your data comes in pairs. For instance, I think twin studies are pretty neat. So here you've got potentially maybe you're testing the effectiveness of some product, I don't know, but you might have one member of the twins be exposed to the treatment and the other twin is serving as a control group. They may be exposed to the placebo. You'll have two sets of data, i.e. pairs of data, and so the selection process was not independent, right? These data sets would be coming in sets of pairs. Another scenario in which you might get paired data is sort of like a before and after study, where maybe a single subject is exposed to a treatment, and we want to compare the response variable before the treatment was administered and then afterwards. So again, you would be having two sets of data, but those sets of data came as a pair from the same individual. So let's take a look at an example that we already saw and see that we have met these requirements. So in the previous video, we looked at the example of two sets of abalone that were measured, their lengths were measured at different depths. And now here I don't actually have the raw data. I didn't show you the raw data, but I've described the sampling protocol to you in class, in which we can assume that the sampling was done randomly. I'll make a note of that here. So we might assume that the sampling was random. Assume random sampling was used, since it wasn't overtly mentioned. Now, it does not appear that these two data sets came as a pair, right? We've got this set of data from the 20-foot depth of abalone and this completely separate data set from the 50-foot depth. They did not occur in pairs. So here we would have independent sampling, independently selected samples. Also, if there was pairs occurring, we would have the same sample size for each one of these, right? These are different sample sizes. So that would be one clue that you've got pairs as well. Now, we don't have the raw data as mentioned, at least I haven't shown it to you, but it wouldn't really matter because both samples take a look at their sample sizes. So both N1 is at least 30 and N2 is at least 30. So that satisfies the requirement of having a normally distributed sampling distribution. So that satisfies the, I'll put it in quotes, normal requirement. We will look at these requirements in more detail in the next lab. That will be Lab 8.